Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis taken by Professor Krishna P. Kaliappan from the Department of Chemistry, IIT Bombay. My name is Srilakshmi S. I am the TA for this course, Classics in Total Synthesis, and I am a PhD scholar doing my PhD in Department of Chemistry, IIT Bombay. So this is our 12th week tutorial session, and so far we have discussed several assignment questions and other related reaction mechanisms, lecture topics, as well as other problems as well. So today, since in the last week we were discussing this week 10 assignment, so the last question we discussed in the week 10 assignment was this one, which is a major product formed in the reaction given below. So this compound, upon treating with the samarium iodide, acetic anhydride, and THF, which will be the major product, that was the question. So this we have already seen in the last session. Now moving to the next question, identify the major product of the following transformation. So here the question is, this compound upon treatment with this tertiary butyl hydroperoxide, this titanium tetraisopropoxide in DCM, and in the second step with BF338 and this uh, trifluoromethane sulfonic acid in DCM, which will be the major product here. So four options are given here. You have to identify what is happening in the first step as well as in the second step. So I will give you a couple of minutes to think about it. So here what is happening? So it is starting from this one. So under this tertiary butyl hydroperoxide and titanium tetraisopropoxide, this double bond will get converted into this epoxide. So it will be, this epoxide will be coming forming from the same side as that of this hydroxyl group. So this is a hydroxy directed epoxidation. So in the first step we will be getting this product, and then what happens when we are treating with this BF3 etherate and this methane sulfonic acid, it will coordinate with this Lewis acid. This oxygen lone pairs can coordinate with this Lewis acid. So this bond will come over here, and then this bond is breaking, and it will come over here, and this oxygen will this bond will break, and it will become OH. So this will come over here, and this bond will break from here, and it will attack at this center. Then this epoxide ring will open to form this compound. So that is happening. So the correct answer here would be option A. Moving to the sixth question. What is the major product formed in the following transformation? So this compound upon treatment with red aluminium toluene at minus 78 degrees Celsius, which will be the major product out of the four options given here. So here, what is happening? This red aluminium will, So here what is happening, this red aluminum is reducing this ketone as well as this ester, and as we can see this all are directed by this hydroxyl group which is already present here. So the other two hydroxyl group will be also having the same stereochemistry as that of the already existing hydroxyl group. So the correct answer here would be option C. The next question is identify the major product formed in the reaction given below. So this phenyl selenium anhydride in the presence of potassium tertiary butoxide is the first step, and in the second step only with potassium tertiary butoxide. So what can happen to this particular compound upon these two conditions? So which will be the correct answer? So here what will happen, this a hydroxyl group will be formed by the in the first step at this position, and then in the presence of potassium tertiary butoxide, this ketone will get converted into hydroxy group, and this hydroxy group will become ketone, like a keto enol tautomerism, like a kind of tautomerism we can say. So the correct answer here is option A. So the next question is, identify the major product in the following transformation. So here this particular compound upon treatment with this potassium tertiary butoxide, oxygen, and this triethoxyphosphane in THF, and in the second step by treating with this ammonium chloride, which will be the major product formed here out of the four options given. So this is the compound. So in first step what can happen, and in the second step what can happen. So basically, what is happening here is an alpha hydroxylation is taking place. So this alpha position to this ketone will get hydroxylated. So this position is already blocked. So there is no possibility of a hydroxyl group at the center due to the presence of this alkene. So this center is free. One proton is there. So there hydroxyl group will get installed. So that oxygen is coming from this O2 source. So this two condition is used for the installation of a hydroxyl group at this alpha position of this ketone. Now, moving to the ninth question of week 10 assignment, identify the major product of the following reaction. So, this compound upon treatment with this quinoline type of moiety in DCM solvent, which will be the major product formed here. So, here, as we seen earlier, this transposition we can say is taking place. So this OAC is coming to this center and this ketone will come to this center using this particular reagent. The correct answer is option A here. Moving to the last question of this week 10 assignment, identify the major product in the below reaction. So this methoxybenzene on treating with this particular anhydride in aluminum chloride in DCA, which will be the major product here. So this is an example for Friedel-Crafts acylation, we can say. So this compound, this will open up, and in the presence of aluminum chloride at the para position, this Friedel-Crafts acylation will take place, giving this compound. So the correct answer is option A. The favorable position is because of the OMe, para position would be favored more for this Friedel-Crafts acylation. So now we will move on to the discussion on week 11 lecture content. So the first two lectures of the week 11 was about eleutropin, lecture 50 and lecture 51. So in lecture 50, we have seen the application of intramolecular acetylene addition, novenagel condensation and glycosylation in the total synthesis of eleutropin by Niccolo. So these eleutropins are anti-cancer agents with an anti-tumor agent with a mechanism of action like Taxol. It was isolated from Eleutropia species of marine soft corals collected in Indian Ocean near Bennett's Shoal in Western Australia. Eleutropin poses significant cytotoxicity against a variety of cancer cells. Eleutropin was shown to be a potent cancer cell inhibitor with an IC50 range of 10 to 50 nanomolar in vitro against a diverse panel of tumor tissue cell lines. It was found to stabilize microtubules by competing for the paclitaxel binding site on the microtubule polymer. The tumor tissue selectivity of eleutropin determined in the National Cancer Institute's 60 cell panel showed an approximate 100-fold increased potency towards selected breast, renal, ovarian, and lung cancer cell lines. So the major structural challenges associated with this natural product is it is having, as we can see, a tricyclic ring which is having 6 9 5 membered ring structure with chiral centers in the core structure. So the construction of 9 membered ring with 6 substituents is a structural challenge. Then in total it is having 10 chiral centers. Then it is having two side chain residues. One contains EN6-methyl urocanic acid residue and the other a betalain 2 2 double prime O acetyl D arabinopyranose unit. This one. So the first total synthesis of this eleutropin was reported by Nicholas group in 1997, and this chemical synthesis allows assignment of absolute stereochemistry of eleutropin. Then intramolecular addition of acetylide, reduction of triple bond and subsequent cyclization was used to form 5 and 9 membered rings. And they started their total synthesis with commercially available monoterpene, that is plus carbon. So this AB ring is 6 9 fused bicyclic system, BC ring is 9 5 fused bridged bicyclic system. This A, B, C is 6 and this 10 fuse system. So the key reactions involved in this total synthesis are novenagel condensation, intramolecular acetylate addition and esterification. And they completed this molecule in 27 steps with 0.9 percentage of overall yield. Then in lecture 51, we have seen application of Nosaki-Kishi ring closure, pyranose to furanose transportation, and Stille coupling in the total synthesis of eleuthrobin by Danishevsky's group. So Danishevsky and co-workers accomplished the total synthesis of eleuthrobin in 1998, starting with R minus alpha philandrine. The synthesis rigorously proves the relative stereochemical relationship of the diterpenoid and carbohydrate domains of eleuthrobin. And the key reactions in this total synthesis involves Nosaki-Kishi ring closure to produce a furanophane, pyranose to furanose transposition, Stille coupling for joining the two domains. This Nosaki-Hiyama-Kishi reaction is a nickel-chromium coupling reaction forming alcohol from the reaction of an aldehyde with an allyl or vinyl halide or triplet. Inter and intramolecular versions have been reported, which have additional importance when this methodology is applied to natural product synthesis. The organochromium reagents formed are unisolable from the corresponding halides and chromium 2 chloride or chromium chloride LAH. So that is Nosaki Hiyama Kishi reaction. And this Danishevsky group started their total synthesis with R minus alpha philandrine and they completed the total synthesis in 26 steps with 0.25 percentage of overall yield. The next lecture, lecture 52, was about 4-ball. So there we have seen the application of oxidopyrrolium alkene cycloaddition in the total synthesis of 4-ball by Venter's group. So this 4-ball structure is given here. This was first isolated in 1934 as the hydrolysis product of croton oil, which is derived from the seeds of purging croton tiglium. However, the structure of 4-ball was determined only in 1967. The four-ball esters have been vigorously studied over the past half century since the discovery that these non-carcinogenic compounds amplify the effect of certain carcinogens in animals. It is proposed the four-ball ester promotes active protein kinase C, a key enzyme which mediates cellular signal transduction initiated by numerous effectors in, including hormones, neurotransmitters, growth factors, and oncogens. As a consequence, this pathway and the four-ball esters have emerged as important leads in the formation of a molecular mechanism for carcinogens as well as in the development of chemotherapeutic agents for cancer and other diseases, most notably including AIDS. Venter et al. Reported the first total synthesis of four-ball in 1989, starting with furfuryl alcohol. The problems posed by the eight stereogenic centers of four-ball and exacerbated by its congested and highly reactive functionality have each been selectively solved with 93% overall stereoselectivity. And one of the key reactions involved in the some of the key reactions involved in their total synthesis are Akhmatovich rearrangement, oxidopyrrolium alkane cycloaddition reaction, which was carried out to get 5-6 fuse ring system of four-ball. And they completed the total synthesis in 53 steps with 0.19% of overall yield. Moving to the next lecture, which was about periplanon. So there we have seen the application of anionic oxycop rearrangement in the total synthesis of periplanon by Stills and anionic oxycop rearrangement intermolecular 2 plus 2 photocycloaddition in the synthesis of periplanon B by Schreiber group. So in 1952, it was reported that a constituent of excretions from female American cockroaches of the species Periplaneta americana is an extraordinary potent sex pheromone. Early attempts to isolate and characterize the active compounds were hampered by because individual cockroaches store only minute amount of hormones, which is pheromones, which is very less than even 1 mg, and a full 25 years elapsed before Persons et al reported the isolation of two extremely active compounds, periplanon A and B. Firstly, in Still's total synthesis of periplanon B, this synthesis provides a striking demonstration of the power of anionic oxycop rearrangement for the synthesis of cyclodecanoid frameworks. The flexibility of this organic synthesis allowed the preparation of three different diastereomers of periplanon B and conclusively established the structure and relative stereochemistry of this molecule. Still's periplanon B synthesis provides a striking demonstration of the power of anionic oxycop rearrangement for the synthesis of cyclodecanoid framework. In this beautiful synthesis of periplanon B, Still demonstrated a classical aspect and use of total synthesis for the unambiguous establishment of structure of natural product. The starting material used by Still's group for the completion of periplanon B total synthesis is ethoxyethyl ether of 5-hydroxymethyl cyclohexanone. And they completed this total synthesis in 15 steps with 8.92% of overall yield. Then in Schreiber's total synthesis of periplanon B, in 1984, Schreiber and Santini developed an efficient and elegant synthesis of periplanon B, which is a potent sex pheromone of American cockroach Periplaneta americana. And in Schreiber's approach to periplanon B, it takes full advantage of facility with which functionalized 5-cyclodecane one-on systems can be constructed via anionic oxycop rearrangements of readily available divinyl cyclohexanol, and the starting material they used was 4 isopropyl 2 cyclohexene 1 on, and they completed this 30 total synthesis in 13 steps with 1.75 percentage of overall yield. So that was about periplanon. Now the last lecture of week 11 was about discodermalide. So there we have seen the application of Corey's asymmetric induction in the total synthesis of minus discodermalide by Schreiber. Boron mediated aldol reaction, the total synthesis of plus discodermalide by Pearson's group. So, scientists at the Harbour Branch Oceanographic Institute have reported the discovery and structural characterization of the marine natural product discodermalide. This compound inhibits the proliferation of cultured lymphocytes, making it a candidate for use in immunosuppressive therapy. Schreiber's total synthesis of minus discodermalide. This was the first total synthesis of minus antipode of discodermalide in 1993. The plan for their synthesis hinged on the recognition that these fragments of roughly equal complexity are separated by olefinic units in discodermalide, and the starting material they used were methyl R3 hydroxy methyl propionate, and they completed this total synthesis in 24 steps with 3.2 percentage of overall yield. So that was about the week 11 lecture contents. Now we will see the mechanism of some of the this novenantial condensation. So novenantial condensation is basically the reaction of this ketone with an activated methylene compound in the presence of an amine base. An alpha beta unsaturated compound is forming. So first what is happening, this amine base will abstract proton from this active methylenated compound, and that will give this enolates which are stabilized by these structures. Then this nucleophilic attack on the carbanion belonging to the carbonyl of the ketone. This enolate ion will attack over this center to form this compound. Then again, this O minus will take proton from this protonated this pyridine. So it will form this compound. Then elimination reaction can happen, and that can result in the formation of this alkene. So alpha beta unsaturated compound is forming. So this reaction is known as novenagel condensation. So you may quickly go through this reaction as well as the lecture contents. So now let's move on to the week 11 assignment. So the first question of week 11 assignment was identify the major products P and Q formed in the following sequence of transformation. So this particular compound, firstly it is treated with this methyl chloride and triethylamine in DCM. We will get a compound P. Then it is treated with the sodium naphthalide in THF. So we will be getting a compound Q. So which will be the corresponding P and Q out of the options given here? So here what is happening, for in the first step this hydroxyl group will get methylated and this will form. Then in the presence of the sodium naphthalide, this OMS will leave, so this bond will come over here and this epoxide will open to form this corresponding allylic alcohol. So the correct answer is option A. Now moving to the second question, identify the major product formed in the following transformation. So this particular compound upon treatment with this thiophenol and SnCl4 in the first step and then with K2CO3 methanol, which product can form? So four options are given here, out of this which will be the correct answer. So here, what will happen in the first step? This anomeric position of this acetyl will get deprotected. Anomeric position of this compound will get deprotected, and there this thiophenol group will be coming. So this will happen through the formation of an oxonium ion intermediate. And then in the second step with K2CO3 methanol, all other acetate group will get hydrolyzed to form this triol. So the correct answer is option C. So firstly, this oxygen lone pair will fall over here. This acetate group will get eliminated, and here double bond will come. Then this SPH minus will attack over this center opposite to this OAC phase. So that will come above only. So this will be the correct answer. Moving to the next question, identify the major product in the following transformation. So this particular compound upon treatment with this chromyl chloride 5 equivalent and nickel chloride 1 equivalent in DMF, which will be the major product here? So here, this is we have already seen this mechanism. This is kind of a coupling reaction or Nausaki-Hiyama-Kishi reaction. So I have shown you the mechanism for this previously. So this center and this center is getting coupled. So we will be getting this correct answer, option B. Now the next question is, which is the major product formed in the reaction given below? So this particular compound, upon treatment with this catalytic amount of paratoluene sulfonic acid, which is hydrated in methanol, which is the major product here? So here what is happening? Firstly, this catalytic amount of paratoluene sulfonic acid can protonate this oxygen, so it will form this particular intermediate. Then this OTMS, this lone pairs will fall over here, and this bond will break, and this will form an OH group at the center. Then what is happening? Again, this hydroxyl group is there, so that oxygen lone pairs will attack at this carbon center, and this bond will shift to form this furan type of ring system. So here the correct answer is option D. Moving to the next question, identify the major product of the following transformation. So, this particular compound upon treatment with this TMS, CN, and zinc iodide in the first step and in the second step with dibalech in toluene solvent, which will be the major product formed here. So, here what is happening? With this TMS, and zinc iodide, this 1 2 addition is taking place. So this will be converted into OTMS, and this CN minus will attack over that center to form this intermediate, which can be written in this form as well. So then, in the presence of dibalech, the reduction of the CN will take place, and the CN will be converted into this corresponding CHO. So the correct answer would be option A. So here the reduction is being stopped at this aldehyde stage by dibalech. Maybe one more question we can discuss in this session. Identify the major products P and Q formed in the following transformation. So here first step they are treating this compound with SOCl2 propylene oxide and diethyl ether, and then they are getting a compound P which they are treating with the silver sort of this benzoic acid, then potassium benzoate and TMEDA in acetonitrile solvent. They are getting another compound Q. So you have to identify which is the P and which is the Q among the options given here. So here the correct answer is option B. So what is happening here? Firstly, with this SOCl2 and this propylene oxide, this double bond, this allylic alcohol is getting, this is eliminating, so this will shift to here and this will attack over that Cl, and we will be getting this compound. So Cl minus will attack over this will go here, and OH minus will leave to form this compound. Then in the second step, what is happening, the Cl is getting substituted with this OBZ or benzyl group. So the correct answer is option B. First is this Cl minus will attack over this center, this bond will shift over here, OH minus will eliminate. Then in the second step, this substitution of the Cl with this benzoate. So the correct answer is option B. So with this, we will conclude today's session. I hope it's all clear. So we have solved week 10 assignment and week 11 assignment, six questions in this session. And we have also discussed week 11 lectures as well. So we will be having one more tutorial session maybe in the Wednesday. So there we will be discussing the remaining questions of week 11, and we will discuss the last lecture, that is week 12 lecture slides, and then week 12 assignment as well. So with that session, we will conclude our tutorial session for this course, Classics in Total Synthesis, for this semester. So if you have any doubts regarding any of the lecture contents or assignment questions, please do let me know. We will try to solve that. So thank you for listening and thank you for joining. See you in the last tutorial session. Thank you.